I'm Arthur Francis Tiban. Today we're going to be dealing with synthesis and probably retrosynthesis. Synthesis basically is just creating a pathway in which a new product can be formed. For example, if we use, we get quinine from a particular tree, which we use in curing, let's say, malaria, and we realize that for us to be able to get that product in quantum, which will serve the whole world, it needs a whole lot. So that obviously will not be enough. So as scientists or as chemists, we create a pathway in which this particular quinine can be produced in the lab without us going to harvest it from the bush or from the bushes. So that is all about synthesis, where we create that path, the procedures required and whatever the reagents are that we can all combine to get what we want. Now, in our course of discussion today, we're going to be focusing on the various aspects that make synthesis easy. Most especially, most of the compounds have to do with benzene, started with benzene. So because of that, before we go directly into synthesizing certain other compounds, we will first of all start our discussion from maybe benzene electrophilic substitution reactions of benzene, which from there we can get a whole lot of compound, which when we affiliate with benzene, we get what we want. Like chloroquine, you must start from benzene. So let's start our discussion from there. We're going to look at, on diazonium chloride. That is a compound that gives us variety of other compounds. We're able to get our diazonium chloride. From there, we can get tons of various other compounds. It's a wonderful compound altogether. Then we likely going to go down into the synthesis by synthesizing few or two other compounds to see what we can get all cumulatively. So let's start with electrophilic substitution reaction. In electrophilic substitution reaction, we deal with electrophiles. Electrophiles are positively charged ions or molecules that are being attracted by the negatively charged side. For example, a benzene ring will obviously attract an electrophile when it gives out one of its electrons to become negatively charged. As such, the positive electrophile can easily go in, and so on and so forth. We also have the nucleophiles, but today, I think we concentrate on the electrophiles. So let's take, for example, if we have our benzene, this is our benzene, all right? And this is my electrophile, so it's positively charged. So if I want to react this with this, first of all, there will be my bond movement here. If that happens, this compound becomes this. Remember, I have moved out this electron to here, so here I have my hydrogen obviously, which is always there, and here becomes negatively charged. Here is positive, it has given out, so it's deficient now. I have my my double bond and my double bond. So, because of this negatively charged position here, the electrophile which is positively charged will obviously have to come in. Don't mind my movement. We obviously have to come in here. And that will give us this. That will now give me my electrophile will be here, and my hydrogen obviously here. And now this is my positive, this and this. When many other steps which will be taken from the canonical set, you will see how this guy will have to come in here finally, which will give me my benzene ring back in its form. I'll show you how that works. But for the time being, and this become my reaction. The reaction now, this is the electrophile. That electrophile could be CH3, could be bromine, could be chlorine, and so on and so forth. NO2, NH2, all these amino nitro groups can all come in here as electrophile. So let me take, for example, let's start so that I can show us the canonical set, how the canonical set works, and how these whole guys can come into play. So now let's take our first example. Alright, in our first example, I have my benzene ring. Plus the electrophile. Okay, this moves down here. And that will give me, I now have my benzene. This has gone, I have positively charged here, and the electrophile is, let's call it is here, and here is hydrogen. Of course, you know that this is the official structure of benzene. It has all hydrogens there. My not putting them doesn't mean that we don't know, we know. The hydrogens are there. That's C6H6. That's the molecular formula. So this is how it is officially. So having displaced it this way, the hydrogen is always there. And since I've taken this out, I am left with this and this. Now in the canonical structure, this is equivalent to this. This bond will move down here, and I'll have this. And I have this, and here is positive now. Here is my E, and here is my hydrogen. This bond will move down here. I have this. Okay, where is it? This bond comes down here, so this is where it is. And it moves from here, so here it becomes positive. And this is it. And here's my double bond, and here I have my E and my hydrogen. So finally, this will come down here. So the canonical set structure is complete. Here I have minus H. So when that happens, I will have my compound becomes this, which is now this, and E, which is the electrophile. So this E represents all aspects of the electrophiles that are going to come in, which we are going to display. So this is how it goes. So in the subsequent reactions, which I'm going to go with, if I show you how nitro group moves, I don't need to start showing the canonical set in here and how the hydrogen comes down. This should be able to explain that with this, we can use this to do or deal with whatever we want to deal with. So this is our first example. So let's take a practical example and see how that works. So we should start with acylation reactions. So let me take this out now. So in acylation, let's call it one. This is my benzene on it. And this, I have CH3Cl, I have aluminum trichloride, and this will give me this. When that goes, I know too well that this is what I'm going to get, CH3 here. This is what will happen. So, you know why I've displayed this before, but you should know, but how do I get this? From the reaction, if I react this, aluminum trichloride will take this, become aluminum tetrachloride, and my CH, let me call it aluminum tetrachloride plus CH3 deficient, the plus. So this plus will take in the negative if I move this. Remember, from the canonical set, this becomes negative and hydrogen, so this one will come in here. So that is how I got here. Now, the formation of bringing the hydrogen to cover this, I've shown us in the canonical set. So I don't need to be repeating that in order for us not to waste much time. But I will, in due time, show us one other two when we want to talk about the E2, that the electrophile here directs where the incoming group comes in. Where you are having one electrophile and I want to react with another, where will it go to? So we'll begin to check at the ortho, para, and meta directions where that goes. So this is it for my acylation. So we can go on and on. Let's deal with, let's call it acylation. The acyl group too. So in this case, I have also my benzene here. We react with CH3COCl. I still have my aluminum trichloride here. we'll take out this to become tetrachloride and this become positively charged. Remember that. So this goes this way. I have my base. The acylation that comes in, I have my C double bond O and my CH3. This is the electrophile. CH3, C double bond O. So now, remember, it is deficient. So this becomes plus. Carbon is tetravalent, but now I have 3, 1, 2, 3. So this is the plus. And that plus now, which is here, will take in the negative 5 from the canonical set, which I've shown us earlier on. And in case, let me just do that, a simple one, so that in case you've forgotten, you remember. This is it. When this moves down here, this gives us this. Here become my hydrogen and negatively charged because it's overcharged. Here it's uncharged, here and this. So when the electrophile comes, which is positively charged, will obviously attack the negative charge. Remember in science we say unlike charges attract, positive, negative will attract, similar charges repel. So this is the different charges, the positive and the negative will attract. So it will attack this position to give us this. So now 1, 2, 3, 4, my carbon now is tetravalent. So that reaction is complete. So let's move on. That is acylation. Let's look at nitration. In nitration, I still have my benzene, remember, as the starting material. This gives me HNO3 and H2SO4. When we react that, we're going to get our NO2. NO2. This is it, the electrophilic substitution of nitration. This is what you get. We have chlorination, we have bromination. All of that will still give us the same thing when we undergo that process. But now, how will you know? We talk about the auto. Let me explain that a little bit now. Okay, this is yes, nitration. Let's talk of amination. Reacting with the amino group. That is a process that is very important, which we're going to look later into. Let me just call that 4, which is amination. Now, amination is not a direct process. We have to use one or two catalysts to convert what we're dealing with down to that amino group. This is the process. Let's just take from here. This I go with nitration first, which is my HNO3 and H2SO4. This gives me this. I have my NO2. When I react it with in the presence of HCl, that will convert the nitro group into an amino group, NH2. So you have to take note of that. So in case you are being asked, you can't get this direct for a direct reaction, but through the conversion of the nitro group, you can get the amino group and you move on. And many other reactions that will come forth to move it to where we're likely going to appreciate further. So that is that about amination. Now, let's look into this amination, for example. If I have a compound where I have my amino group in it, where will the next, when another compound is coming in, where will it go to? It is very important. By so doing, you will know whether it is auto-para directing and so on and so forth. So about the auto-para, let me just explain a little bit before I can proceed further. So this is my benzene group, my benzene compound. This, and this. Any position that is being taken becomes your position 1. So if I put anything here, this becomes 1. If I put anything here 1, here becomes 1, whatever it is, the first group. So let me call this NH2. This is my my position 1. So this becomes 2, 3, 4, 5, 6. Or vice versa. Now, having gotten this, if I decide to react this with HNO3, H2SO4, I'm going to get a nitro group, which is going to come into the same ring. Now, where will this nitro group go? It can't just go anywhere. So that is where we talk about the auto-para directors, the metal directors, and so on. Some of them with activation, some with deactivation. It is very important as that. So, how do we know, or how are we going to know where it's going to go? So let's look at this. Alright? So, first of all, don't forget, this is auto. These two positions, this is my 1, these 2 become auto. This is metal. These 2 positions become metal, and this is para position. So, the question now is, the incoming group, which is the electrophile, into this, is it going to go to the auto position, or to the metal position, or to the para direction? You can't just put it anywhere. You have to carry out 1 or 2 other reactions to know where it's supposed to go. So let's take that, for example, this is the nitro group. Let me take this out. I want to find out where the incoming electrophile will go when I have 1 already in there. And that one that is in there gives us prescription where the next one will go. So let's proceed and see that. This. Now, for me to know where another one is going to go, I have to elucidate on the canonical structure. From there, I can easily predict. So, this move down here. I have this now. On my structure. And I have double bond here, NH2. Now, as this one comes down here, this one obviously, not because if I leave this here, because 1, 2, 3, 4, 5. As that comes down here, this one will move down here. So now I have here, obviously 1 here, 1, and here become minus. Because this one moved down here, that becomes minus. Okay, I move down again. So if this is minus, if I move, this is auto. If I move this one here to this place, this becomes positive. Or better still, I move this one here to cover this position, and this one will move. So now I will have this. This is my NH2, obviously. So this is coming down here, and this will have to move to here. So remember, this one is here already. So this one coming down here, this is it. Alright? Then this one is moving down here. It becomes this, negative here. Now I'll move again. My NH2 is here already. So this is what I'm having now. If I move this one here, I can now move this one here. So when that happens, this one is here already. This one moves to this place, which is here. And this one moves down here, which becomes negative charge. So, and this is what I have in the canonical structure of that amino group. So what does that mean? It tells you that wherever you see the negative, that is where the incoming electrophile will go to, which makes an amino group auto and para directors with activation, because whatever is coming in goes in with speed. As such, that becomes so perfect. So in that sense, whatever comes in will either go to the auto group or to the para position. Let us look at another member, another group, electrophile perhaps, and see where that one goes to. Then we can easily conclude. So we can move back from here to something else. So let's take another one. NO2. Now, this is how the nitro group obviously is being displayed. Let's see what happens here. This will move down here. The next step, this comes in here. And this will move up here. So I will have a compound like this. Now, this one hasn't moved. Give this positive. I now have double bond here because I've moved one of it down here. I have my nitro. This is O negative, O negative. Now I still have my this and this. So this is at the auto position is positive. I'll explain that. Let's move on. Then this one will now go here. Alright, I have my double here, O negative, that one is a constant. So this one has moved down here, I have here and here, but here becomes positive. Then, lastly, this moves down here. I haven't done that. I will now have this. I have a bond here, I have another bond here, I have positive here. And now, all the positive signs you see tells you that reaction cannot take place in there. Why? Because they are all electrophiles. This is positive. Electrophile is positively charged. We're dealing with electrophilic substitution reaction, remember? So, and what we're dealing with, we have, let's call it CH3 positive here. This is positive. It cannot go to a positive sign. We say similar charges repel. So it doesn't work. So now, at the auto position, we have positive. At the para position, we have positive. The only positions that doesn't have anything are the meta positions. These meta positions. They are the only ones that are free in this whole canonical set. Which means that if a nitro group is taking the position 1. Whatsoever comes in again goes into the what? Meta position. There is no sign. So we call it, it is meta directing with the activation. Why? It is not activated because if it was negatively charged, it would be activation because the positive can easily, quickly just go in. But now there is no sign there. But then it can still go to these positive signs, which are similar charges, you obviously rebel. So it will now go toward this particular position. So they are meta directors with the activation. The amino were auto-para directors with activation. The methyl group is also auto-para with activation. And so on and so forth, many of them, as we will see. But today we're not dealing with that. We're looking at synthesis. How then do we proceed to get what we want? If we don't know how to do this, we will obviously have a problem. I think you will get that picture clearer when we get into synthesis fully. So for the now, let us move to, how they call it, diazonium chloride. Now, like I said, diazonium chloride is a compound which through it we're able to get numerous other compounds through just a little reaction. But now how do we get the diazonium chloride? Now let's proceed. In getting the diazonium chloride, we start from our official benzene ring, which is this. I'm trying to economize the board so that I can cover a whole lot of space. Okay, I have this. Nitration, which will first take place. H3, H2SO4. Give me this. Alright, I have my NO2 here now. When this goes within the presence of HCl, I'll change that to amino. H2. let's go with nitrous, presence of HCl, it will convert that into benzene diazonium chloride. So this will give me N2Cl-, this is plus, and I still have this, this, and this. So this is benzene diazonium chloride. So this guy is very important. It's one of the most important compounds when we're dealing with synthesis. Now, what do we do with it? Certain other reactions that goes on here, you see a whole lot of changes. Permit me to start. So now we know how to get this. I want to clean this whole thing, bring it to the middle, so I'll be able to expatiate efficiently. So let me take out this so that I can bring it in the middle. We now know how to get our benzene diazonium chloride. That is settled. So let's see what happens next. Here, if I react this with water, I will have phenol, OH. If I react this with H2PO3, that is triazophosphate 5 acid, I can form another benzene. If I react this with copper nitrate, I will have a nitro group. And if I react this nitro group with thing in the presence of HCl, I will have amino group, NH2. See how important this guy is. If I react this with copper chloride, okay, in the presence of HCl, I will have chlorobenzene. If I react this with copper bromide in the presence of hydrogen bromide, I will have bromobenzene. What again? If I react this with potassium iodide, I will have iodobenzene. If I react this with another benzene, C6H6, I will have a biphenyl. I'll have a biphenyl. And so on. You see how important this compound is. Benzene diazonium chloride. Because through it, we'll be able to get numerous other compounds which could be starting reagent for whatever we want to deal with. Like phenol, for example, where is the guy? This is phenol. It's so important that if you want to deal with the synthesis of paracetamol, you must start with the phenol. This is the structure for paracetamol. So you have this now, OH. This is nitro group. This is what you get, CH3. Now, we know that phenol, the OH group, is para-directing. So, when I have this phenol, I can now bring my nitro group, which is this, react the nitro group with this to get amino, which gets me here. Then from here, I react with ethanoic chloride. I can get this to complete. So, if I do not know how to get my benzene diazonium chloride, definitely I will not get my OH. Then how can I now synthesize my paracetamol where the starting reagent is phenol. So it is imperative that this plays a key role in our discussion today, and you must take into cognizance that this whole stuff you see here, and many more that I can, because of space, which I cannot bring out, there must be the first thing, or the first thing in your head, so that by virtue of that status quo, you'll be able to proceed without hindrances. So, okay, if this is it, so let's move down to Grignard reagent. Grignard reagents are powerful reagents because they also enable us to achieve a lot in the course of our synthesis. We've not started the synthesis officially. I'm only showing us how we can get starting what reagent, which will enable us to synthesize any compound we want to synthesize. So let's take this out and go to the Grignard reagent. Grignard reagents are sometimes called acyl magnesium halides. They are very important organometallic compounds which are very reactive with most of these inorganic compounds like water, methane, carbon 4 oxide, oxygen, and so on and so forth. By virtue of the Grignard reagent, it brings us closer into what we need and how to go about that. So let's see, how can we prepare them? Now we have this acyl magnesium halide. Let's call it X as our Grignard reagent. I will explain this. Now, the arc here could be CH3, could be CH3, CH2. My magnesium is there. The halide, let's take chlorine. This is a Grignard reagent. We're going to look into its reactions. Now, first of all, before we get into the reactions, how can we get this? How do we get a Grignard reagent? That is very important first. So, let's start. Have in mind that this is the definition for it. So, whatever we're dealing with, you don't lose sight of this reality. This is where we're going to. Okay, let's take, for example, we have RMG. No, let me just use the reagent and not this figurative stuff. My CH3 magnesium will react CH3 halide, let's call it chlorine, chloromethane, in the presence of dry ether, okay, plus magnesium. The presence of dry ether will give me CH3 MgCl. This is methyl magnesium chloride. So this is now my Grignard reagent. So this is the reaction. I react my magnesium with a chloro compound, chloromethyl or chloroethyl or propyl and so on. In the presence of dry ether, it gives me my magnesium methyl magnesium chloride. So let's look at another example of this. We can take CH3, CH2, Cl, chloroethane, plus magnesium in the presence of dry ether. We are going to get CH3, CH2, MgCl. So this is ethyl magnesium chloride. This is another one. If I use a propyl group here, I get it there. And so on and so forth. This is how we produce our Grignard reagent. So now let's look at the reactions of Grignard reagent. Okay, this is my reagent now. Let's react. Reaction with water. 1 with water. Okay, I have my CH3 Cl Mg, as the case may be, plus hydrogen hydroxide. Remember, that is water. Hydrogen hydroxide, that's H2O, which is the same thing as this. So hydrogen hydroxide is water. So when I take this out, In the course of the reaction, in the presence of dry ether, I will have CH3 and hydrogen. It takes the hydrogen plus magnesium hydroxide OH Cl. This is what I get. So the reaction with water, this is what I get. So let's take another reaction with amine. That is a amino group. I still have my CH3, CH2, MgCl, which is my ethyl magnesium chloride, reacting with, and okay, not amine, ammonia. Let's take ammonia, ANN. With my N, let me put it this way, NH2. This is ammonia, which is NH3. If I take this and add it, becomes that. In the presence of dry ether, I will have CH3, CH3. These two takes one of it. Alright? Now I'm left with magnesium NH2Cl. That is with ammonia. But I'd like us to deal with something complicated, like formation of reacting with ketones and aldehyde. I think that is something that is very important.